This is Knowledge Engineering with Semantic Web Technologies, Lecture 4, OWL Rules and Reasoning. Today we want to talk about the OWL general role inclusion. So what does that mean? You all know, in OWL I also can define a so-called R box, where I define knowledge about properties, and in description logics you call them roles. So for example, you can define their property hierarchies, but, and this is new, you can also define complex properties, complex roles, by simply composing it from simpler roles. So for example, you can define an uncle to be the brother of your parent. So if we do property definitions like that, we have to consider the so-called general role inclusion. But the problem with that is we have to make some restrictions. Otherwise, this general role inclusion would lead to undecidability, and of course we want to avoid that. So, complex role inclusion. So, complex roles or properties can be constructed from simpler ones in your R box. We just said that. So, for example, I could say the friends of my friends are also my friends. Yeah, of course, for that I do not really need a general role inclusion, because here it's sufficient if I simply declare that property has friend to be a transitive property. If I declare that transitive, this property, then it means, okay, the friends of my friends are also my friends. Okay, let's look at a variation of that. The foes of my friends are also my foes. Now, that cannot be expressed with the means that we have right now at hand in OWL. So therefore, we must have something with which we can construct a complex role or property to be a foe from foes and friends. So what we want to do here is somehow we want to connect has friend and has foe to become a new definition of has foe. We could also then call that has friends foe, for example, if we want to give it a new name. But the point is cannot be expressed in the way or with the means that we have talked about now. So for that, we need something which delivers us more, or which gives us more expressivity. One way to do that, of course, we know that in first-order logic almost everything is possible. So there we can define it rather easily, so with a rule like that. So you could say there, for all x, y, and z, it holds that if x has friend y and y has foe z, then x has the friend's foe z. So we could define that, but of course exactly that kind of axiom, that kind of rules are not part of OWL. But what we can do is we can construct roles from smaller, more atomic roles or properties. So Schroik-D enables the construction of arbitrary complex roles via general role or general property inclusion. So this is the reason why we have this letter R here also in the name of that kind of description logic. And Schroik-D also is the basis of OWL-DL, which is the basis of the OWL we are talking about here. So what is the general property inclusion? So these are all kind of R box expressions of the form you see here. R sub 1 connected to R sub 2 connected to R sub 3 and so on and so on. And they are a sub-property of the property S. And with this connector, so this circle here, we are connecting the roles in the sense like you see the example below. So has parent can be connected with has brother, and this forms then the role has uncle. The semantics is quite clear, so this is of course derived somehow from first order logic. So if we have two individuals, x sub 0 and x sub 1, and they are both in the interpretation of role sub 1, and we have x sub 1 and x sub 2, and both are in the interpretation of role R2, and so on and so on and so on, and this goes until we have the individual x sub n minus 1 and x sub n, and they are both connected via the role R, or are both in the interpretation of the role R sub n. Then it also holds that the first of the line, so x sub 0, and the last of the line, x sub n, they are both then part of the interpretation of S. Okay, so you have a steady chain, and this chain connects property by property by property by property. And of course, there must be the same individuals. So x1 and x1 you see here comes as the second part in R sub 1 and the first part in R sub 2. So this is really a chain where you connect from individual to individual to individual for which exactly this condition, this property constituent holds. So, for example, with our parent example, if x sub 0 and x sub 1 are interpretation of has parent, which means that x0 has parent x1 and x1 has brother x2, then it holds that x sub 0 has the uncle x sub 2. So this is the way how general property inclusion works. But we have to take care because otherwise it will lead to undecidability. So when is that the case? What do we have to consider here? So one point is R boxes, somehow here, they act like grammars for context-free languages. And maybe you remember that from theoretical computer science. So context-free languages are languages like the one you see here that are, of course, you have usually an alphabet, so a set of characters where you are working with, and then you have a grammar with rules that can be applied to form valid expressions, valid sentences. And you see here a language which consists of the language of the characters A, B, and there always A comes before B, and both are in the same quantity. So it means the language has AB, AAB, AAA, BBB, and so on, and then 4 times A, 4 times B, 5 times A, 5 times B, and so on and so on. This is a context-free language. And usually you could express this with a grammar like you see here on the left side. So you have a non-terminal symbol L, capital L, which can be then mapped to two terminal symbols AB, which are then, of course, part of or already constitute the first sentence of the language. Or you have then a generation rule where also a non-terminal symbol occurs on the right side of the rule. So the second rule here says that L is mapped to ALB. And then again, of course, L can be substituted by the first one, AB, or can be substituted by the second one, and then this expression grows and grows and grows. And this, of course, can easily be translated here also to our expressions in description logics, because the first one corresponds simply to a language where you combine two relations R sub A and R sub B, which then should form a more complex property L. And the second one would put the L in this property chain in the middle. And therefore, you could always substitute L also via the other side or the other part. And then, of course, this somehow relates to each other. And you see exactly then, when you have a non-terminal or something which is here the super property, if this occurs also in the chain of sub-properties somewhere in the middle, this might lead to difficulties, especially if you want to decide whether two properties are disjunctive, for example. Simply because disjunction for context-free languages, this would mean that the intersection of two languages, whether this is empty or not empty, empty it would be if the two languages or the two properties would be disjunctive, this is undecidable. So this is a problem you cannot decide simply because you have infinite number of possibilities you have to consider there. So therefore, what you have to do is you have to restrict somehow the way how you are creating these property chains. So exactly this situation where you have this terminal or this superclass in the middle of a chain is not allowed. Simply what we want to maintain here is we want to restrict also, if we consider it from the viewpoint of grammars and from formal theoretical computer science, then we want to restrict it to a more simpler construct, not to context-free languages, but to so-called regular languages. In regular languages, the non-terminal symbols are only allowed either at the beginning or the end of the right side of the grammar, which means it can only grow in one direction. And then everything will work. You will see that. So R boxes are like grammars for context-free languages. We have seen this now. And the problem here is the emptiness of the intersection of context-free languages is an undecidable problem. And this, of course, if we allow expressions like context-free languages within our property chain, then potentially we would run in infinite loops. And of course, we want to avoid that. Therefore, we restrict the R boxes to so-called regular R boxes. They are related somehow to so-called regular grammars, regular languages. So what do I have to do to maintain regular R boxes? So first one, all property names that I use, they must be ordered. So I must define an order, a strict partial ordering. So this ordering must be strict. First thing, an ordering. We will see how we will use that. And then each R-box inclusion must be formed like one of the following examples. So either I join a role with itself to be its subclasses, so that's the first one. R composed with R is a subclass of R, so this is allowed, no problem. Of course, this can grow, but this does not change. Then, of course, I can define the inverse of a relation or of a role to be a subclass of itself. And then, of course, I can have a property chain where the super property does never occur on the left side. So the property on the right side never occurs on the left side. This, of course, is allowed. But this also holds then for if one of the properties S sub 1, S sub 2, and so on are not atomic properties, but if they are composed, then, of course, R must not be one of the constituents of that roles. So otherwise it would, in the end, then again lead to undecidability. The only way when R is allowed on the left side of this kind of equation is if it's either at the beginning or at the end. So you see this here in the right column of the both. So either R is in the beginning and then R following all these S sub 1 to S sub n, or it starts with S sub 1 to S sub n, and then R is the last one in the chain, which might be then part or constituent of the super property R. So only these are allowed. All others are not regular and might lead to undecidability. And here it's important that all of the S that you have here, they must be smaller than R. They must always be on the other side, as you see here. And only then an R box is called regular if such a strict ordering really exists, if I can order that in that way. So to understand that, of course, we have to look at a few examples. So consider the first one. So first we have R connected to S is a subclass of R. Okay, so here we could induce the ordering that S is on the left side, R is on the right side, so S is of course smaller than R. Then we have S connected with S is subclass of S, so this is allowed, so here we cannot deduce a new ordering. And then we have R connected to S connected to R is a subclass of T, or forms, sorry, not class, is a subproperty of T. And of course, here we have another ordering. We can see here that R is smaller than T and S is smaller than T. And again, we also have from the first formula that we have here that S is smaller than R. Therefore, we can define a strict ordering, and this is nowhere broken. So we can define that S is smaller than R is smaller than T. Therefore, if I have an R box with these three expressions, then it's perfect and it's regular. So this is allowed. Okay, let's look at the next one. This is pretty clear. Here I have T, which is on the right side, also on the left side, but in the middle. And of course, this is a not allowed inclusion according to the rules we had on the last slide. So this is, of course, not regular and not allowed in that case. For that one, it's a little bit more complicated. So we have here R connected to S. This is a subproperty of S, and then we have S connected to R as a subproperty of R. So from the first one, we could deduce that R is smaller than S, and from the second one, we could deduce that S is smaller than R. And this, of course, does not hold. So here you cannot define a strict ordering, but because this would only hold if S is identical to R. And this is not allowed in that case, because then it's not a strict ordering. So therefore, this is not regular and not a valid ordering is possible. So you can see this in an example where I take instead of the abstract property names, these characters, if I name a self-speaking name here, for example, I could say if I connect has parent and has husband, then I come up with something which is has father, which means the husband of a parent is a father. So if I have a parent who has a husband, then this is my father. So this would be the first that you see here. And the second one, I simply would say has father is a subproperty of has parent. So has father is a specialization of has parent. The problem here is, of course, I could say that, and all of these assumptions are valid, but they are not regular, simply because it would enforce first that has parent is, from the first one, smaller or a specialization of has father, which doesn't hold. And on the other hand, we have has father is also, as you see here, a specialization of parent. So here is no strict ordering possible. This would only work if both properties really are the same, but it's not the case. And of course, the ordering must be strict. Therefore, it's not regular. So we have to distinguish between regular and non-regular R boxes, and only property inclusions which fulfill this condition are valid for OWL, because otherwise it becomes undecidable. So we have some further restrictions to maintain decidability, because role inclusion, general role inclusion, is really a rather powerful means if it comes to semantic expressivity. So the first thing is, of course, we also have to restrict somehow the kind of properties on which we apply that. So we have to restrict general class inclusions on properties here. So for example, first simple properties are properties we are considering for the general role inclusion, and in join D, so in the old version of OWL, simple properties are properties without any transitive subproperties. And in Schroik, of course, we have in addition also to consider the general property inclusion, in the following sense that we say simple properties are all properties that, and now it comes, are not on the right side of a property inclusion, and they are the inverse of a simple property, so then it's allowed and it's a simple property, or they are only on the right side of a property inclusion. R is a subproperty of S, where on the left side is only a simple property and not a property chain. So these are simple properties, and for them, of course, special things or most things are allowed, and for the complex properties, then we have to look for restrictions. So the non-simple properties or complex properties, these are properties that are directly or indirectly dependent on property chains somehow. And then the following restrictions hold. So the following expressions in OWL are only permitted for simple properties, which are first the qualified number restriction. So this is not allowed for complex or non-simple properties, simply because this would become too complicated. And as well, it's not allowed to take or to define a property chain to be irreflexive or disjunctive, or to apply it on itself, or to say there is no or a negated property instantiation when the property itself is non-simple. So this is only allowed for simple properties. For non-simple properties, this is not allowed, simply because otherwise the computation of the result would become too complex. It would become undecidable, and we disallow that, so we deny the use of that simply to keep and to maintain decidability. So this is really a complicated part, and for all of them, of course, you have to give a proof for that, but of course the proof here is not part of this lecture, but you can prove that. So this is the main reason to maintain decidability. So to sum it up, to ensure decidability, the following structural restrictions must hold for Schroik D, which is first the regularity. So we restrict the potential interactions of all the available R-box axioms. And the other thing is, of course, it must hold the simplicity of properties. There we have restrictions of how to apply properties, for example, in number restrictions, and which other restrictions can be applied on simple or non-simple properties. So simply to maintain decidability, a number of restrictions arise for the overall structure of the knowledge base that have to be considered then for all axioms, especially for the axioms in the R-box. So this is, of course, the way how we restrict this powerful general property inclusion, which is also referred to as property chains or general role inclusion. To define a property chain in OWL, that's pretty easy. So here, for example, we refer to the first example that we had on the slide. So now I define a new property, which is called has friends foe, and I say this is an object property, and then after that I define this as to be a property chain. So therefore we have a new OWL keyword, which is OWL property chain axiom, and then after that OWL property chain axiom, I introduce simply the members of the list of properties which I want to connect in the order I want to connect them. So first has friends and then has foe. So here I define has friends foe as the foes of a friend. So like you see here. And of course, to define a property chain, this is of course not allowed for data type properties, simply because in property chains you are connecting the chains from individual to individual, which is connected here. And for a data type value, this of course would not hold. So you don't have here a uniqueness assumption, and of course the data type, if it has a value, it's not necessarily an individual. So this only holds for individuals. So it's not allowed for data type properties. So now we have learned a lot about OWL2 property chaining and role inclusion. This is, as already said, a rather powerful tool. The point now is, besides all the restrictions we have heard, or to maintain decidability, is are we now really able to design or represent all the knowledge we want to represent? Or is there something left which we cannot cover, which we cannot tackle with the help of OWL? So we know already first order logic is more complex and also, again, more expressive than description logic. So there must be something which can be expressed there, which is not being able to express it with OWL or with a description logic. And in the next part of the lecture, we will talk about rules, and we will give an answer to the question whether rules are more than description logics.